As a last step, we want to take a look at the three programming models and then talk a little bit about today's supercomputers. The first is shared memory, sometimes called shared address space because the memory doesn't really have to be shared, just the address space does. But in this kind of a system, each processor can address anywhere in the memory, and this is the programming model that's very familiar to us from use in uniprocessor systems. So we're all familiar with writing programs for shared memory, although in parallel systems we need to make sure that the threads cooperate right, and that requires adding some synchronization operations. A little bit different is the distributed memory or message passing model, where a processor can only access its local memory directly, and if it wants to access anything in any other memory, it needs to send a message to another processor. The third programming model is the data parallel model, and you've seen this diagram before as an example of an SIMD machine. In this case, operations are performed in parallel on each element of the data structure. So let's say we have 100 or 1024 processing elements, or PEs, or as ALUs, essentially the same meaning. And these processing elements are all operating at the same time. Then they'd be operating on 1024 different data items, performing the same operation on each pair of operands. So there's logically a single thread of control, but you can think of it as having a processor associated with each of the different data elements that's getting processed simultaneously. The architectural model is having an array of simple processing elements, and we don't call them processors because they don't have a control unit that's used to sequence through instructions. Rather, all of the PEs are attached to a single control processor that issues instructions. And one of the advantages that might not be apparent at first glance is that this is a cheap way to synchronize. You can have 1024, let's say, processing elements that are all working on the same instruction at the same time, and you know that none of them can get ahead of the other ones because they're interpreting the same instruction. So you don't need to do synchronization because they're all working at the same time, and when one stops, they all stop. Okay, so the original motivation is that it matches simple differential equation solvers, which did calculations of this form, as we'll see a little bit later on. Okay, now we want to take a look at the Top 500 site. And the Top 500 site is a website that records what are the 500 most capable supercomputers in terms of flops at any particular point in time. And the list comes out twice, in November and in May, and last I looked anyway, the November list was the latest one, so I'm going to have you take a look at those. But realize that back in 2004, 5,000 nodes was the largest supercomputer and 8 gigaflops. Now, as of the last list, Summit at Oak Ridge was number one. It has 2.4 million cores, which would be, similar to the kind of processors of which there were only 120 in the largest supercomputer back in 2004. Now we have 2.8 petabytes of total memory, which is a whole lot than 10 terabytes, right? It's almost 1,000 times, 250 times as much. And then the max performance, 148.6 teraflops versus 30 teraflops, and that's the peak performance, which is a little bit different from the max performance because the Rmax describes the maximal achieved performance, whereas the peak performance is the theoretical peak performance. Theoretical peak performance was 200.8 teraflops. So the supercomputers now are really much larger than they were back then. And what I'm going to ask you to do is go through and explore the list. So you could For example, look at the top 500 list from November 2019, and then look at the statistics and look at who the vendors are. You would find that Lenovo is the top vendor. If you looked at the architectures, you would find that almost all of the architectures are clusters. Remember, clusters are the architectures that have kind of the most loosely coupled sub-architectures in them, where they're not sharing memory, but rather they're just communicating over a network, a very fast network, yet still communicating over a network. That's the way you build the largest supercomputers today. You might also look at the development over time in statistics and countries. You'll note that China now leads in the number of systems in the top 500, but the US still leads in performance share. So the exercise that I have is to go to top500.org and look at the list and statistics menu in the top menu bar. From the statistics menu, choose one of those things we've talked about, and then just look at it, try to come up with some interesting idea, then submit your results. And once you submit your results, you'll be able to look at the results submitted by other students this semester and last semester as well. So I hope you find some interesting observations. And that's it for today. Tomorrow or on Friday, we'll be talking about parallel programming models in more detail.